Hi, welcome to Unit 3, Day 1, Part 3, Particle Nature and Quantization of Light. So light is quantized, and that may be something that you've heard before, but what exactly does that mean? It essentially means that light is, that a quantum of light is a discrete little energy packet, okay? So rather than a stream of energy, light travels in these sort of quantized energy packets. And the way you sort of can visualize it, if you think of light coming from a sun, you can think of it as just sort of like little packets at certain discrete energies traveling from the sun. And that's different from the idea of like this just continuous stream of light. So how did scientists discover that light was quantized? And there were three phenomena that that were explained by the idea that light had to be quantized. And without having that understanding, the phenomenon could not fully be explained. In the same token, these phenomenon therefore provided evidence that light is quantized. So let's take a look at the three phenomena. The first one is known as blackbody radiation, which essentially is you heat up metal and it emits light. And the hotter the metal gets, the more intense the light that is emitted. Also, the higher the frequency of light that's emitted. So if you think about metal being heated up first, it's sort of this red color, and then eventually it gets this really light whitish yellow color. And the red light having the lower frequency and less intense than the white yellowish color. So scientists were trying to develop a mathematical model to describe and explain blackbody radiation, and they were unable to do so. Like they can do it for certain ranges of intensity and temperature and frequency, but once they went to a different range, that model didn't quite work. And it wasn't until 1900 when Max Planck was able to derive a formula that modeled the phenomenon by proposing that light is quantized, that light is in these discrete energy packets. And so this was our first evidence that light was actually quantized. Now, later, only several years later, Albert Einstein explained the phenomenon of the photoelectric effect due to the particle nature of light. And that was in part based on his understanding of what Max Planck had first came up with, the idea of light being quantized. So because he had the idea that light was quantized, he can visualize light as this sort of particle, a discrete container or energy of light. So photoelectric effect is our second phenomenon. The last one is the emission spectrum. So scientists for a while were studying the emission spectrum of a gas, and the experiment is one where you take an element like hydrogen gas and you pass an electric current through it, and that excites the hydrogen gas, and it starts to give off this light, as you can see here. So the light that was given off was analyzed through spectroscopy. It was passed through a prism and broken down into its component wavelengths. And they noticed that there were discrete energy gaps depending on the element. So hydrogen had a certain pattern, helium had another pattern, etc. And they were trying to explain this. And in 1913, Niels Bohr was able to explain these discrete lines of color in the emission spectrum of hydrogen and other elements as well, as owing to the fact that the energy of an electron is quantized. So what's happening here? When the excited hydrogen atom emits light, what's occurring is the electrons that have been excited, the electrons in the hydrogen atom that have been excited, start to drop down to a lower energy level, because things tend towards a lower energy state. So if you have these excited electrons, they don't want to stay in this excited state. They want to release this energy, and they release that energy as light. So the light that we see the light that's emitted from the hydrogen gas is due to the electron releasing that energy. And because the electrons are releasing a discrete amount of energy, you don't see a continuous spectrum, sort of like a rainbow, but you see these discrete lines, and each of these lines correspond to an electron losing a certain amount of energy. So, for example, an excited electron in the fifth energy shell, if it drops down to the second energy shell, it will release light of a certain wavelength that corresponds to this blue-violet light. On the other hand, if an excited electron in the third energy shell, if it drops down to the second energy shell, emits this sort of red light. And the red light is actually lower energy than the blue light, and that makes sense because the energy gap between the third shell and the second shell is smaller than the energy gap between the fifth and the second shell. So these three phenomena, blackbody radiation, photoelectric effect, and emission spectra, all of that help to contribute to supporting the idea that light has a particle nature and also that it's quantized. It has a certain amount of energy. So a quantum is a discrete amount of energy. So take a moment in your note packet to copy these notes. All right, we've been talking about that light as quantized as a certain amount of energy, but what exactly is that energy, or how can we calculate that energy? And that energy can be calculated through the equation that energy is equal to Planck's constant times the frequency of light. And as you can see in this equation, that the higher the energy, the higher the frequency, the higher the energy, and vice versa. So if we look at our electromagnetic spectrum, where we see that the gamma rays have the highest frequency, that would mean that they also have the highest energy. So gamma rays have the highest energy of light, and whereas radio waves will have the lowest energy of light, because energy and frequency are directly proportional. So let's summarize that through this equation. Energy, which will be calculated in units of joules, is equal to Planck's constant, which is 6.626 times 10 to the negative 34 joules per joule second, times frequency, which will be in hertz as well. Okay, so this equation, energy equals Planck's constant times frequency, of course relates energy and frequency, but what about energy and wavelength? We already know that the wavelength and the frequency are related through the speed of light. So if we combine these two equations, we can get an equation for energy and wavelength. So let's take a moment to do that. First thing we'll do is we'll solve for frequency. We'll solve the speed of light equation for frequency. Then we'll plug that value into our energy. And when we do that, we get that the energy is equal to Planck's constant times speed of light divided by the wavelength. Okay, so now let's go back to CFU2, seeing this relationship between energy and frequency. And I want you to answer CFU2, see if you have not done so already. Pause the video now, and when you press play again, the answer will be revealed. So here's the answer for 2C. All right, there are 3 more CFUs, CFU 4 through 6. So take a moment to pause the video, and when you press play again, the answer will be revealed. So in the first CFU 4, they're asking how much energy in joule does the light from CFU 3 have. You return to CFU 3, you'll have your frequency is 5.09 times 10 to the 14 hertz. Planck's constant is 6.626 times 10 to the negative 34. And we go ahead and we just plug that information in to get our energy. Second one, how is the wavelength of light related to the energy of light? So we can use the energy equals Planck's constant times speed of light divided by wavelength equation. And as you can see here, as you increase the wavelength, since that's in the denominator, the energy, of course, will decrease. So they are inversely proportional. and or indirectly proportional. And so that means if the wavelength is double, the energy is half. Last one, which would carry more energy, a radio wave with a wavelength of 10 to the third meters, or light that has 5.3 times 10 to the minus 28 joules of energy. So in order to do that, we have to either convert the energy to wavelength or wavelength to energy. I decided to convert the energy to the wavelength into energy, so I plug the wavelength into my equation. However, it's important to note here that we didn't need to do any conversion of the wavelength since it was already in meters, and it needs to be in meters in order to use it into this equation. So once we get that, we plug that in, and we see that light with 5.3 times 10 to the minus 28 joules of energy has more energy than the energy of the radio wave. All right, that's it.